guys. So yeah, today we're going to quickly finish off what we were doing on Friday, and then we're going to start looking at the next topic, which is numerical methods. Right. Cool. Let's get rid of this a sec. So I'll quickly go through this, and then we'll take the register in a second. So, write this down into your notes. We kind of discussed this already, but just so you got the kind of more formulaic way of saying it. So a series is increasing if un plus 1 is greater than un. What does that actually mean? Well, it means that a term is bigger than the term before it. Un plus 1, a term higher than un, is bigger than un. So it's increasing if the next term is bigger than the current term. It's decreasing if the next term is smaller than the current term. And it's periodic if a term later on is equal to the first term. So if it goes kind of back round and gets back to the first term, then it's periodic. That's not only true for the first term, or I would have written U1 and U2. It's increasing if a term is bigger than the term before it. It's decreasing if a term is smaller than the term before it, always. And it's periodic if a term later on is equal, or every term is equal to a different previous term. Yeah, so these rules must be true for every single term for it to be increasing, decreasing, or periodic. So I think we've already looked at examples of those three. Just to go over a period again, if we had like, I don't know, 5, 1, 5, 1, 5, 1, that's got a period of 2. It repeats every 2. If we had 0, minus 1, 1, 0, minus 1, 1, that then has a period of 3. Right, so just a little bit on that, and I'm going to do what we're going to do. 2 more questions, and then we're going to move on to the next topic. So, yeah, start with these ones. So I'll give you guys 10 minutes now to do those 2, then we'll have a look through that, do the last question, move on to the next topic. Can you guys comment your names so I know who's here, and can you send me photos of your answers to the Microsoft Teams? People who aren't replying to stuff this week, I'm going to just delete your attendance. So I won't take your attendance if you're not actually, getting involved in the lecture. So please comment. If it's asking for help, that counts. So either ask for help or please send me your answers. But I do want all of you responding this week, otherwise I'll be erasing attendance. So little warning there. Yeah, so I'll give you guys 10 minutes to get started today, and I will take the register. Cool. Right. I had a few questions there. I don't think I've been sent any answers yet. No, I'll quickly invite you all to the chat. So inviting all you guys to teams now. So as I said on the YouTube, you need to work out the first few terms, and we're told that it's periodic, and we're told the period is 2. So if it's periodic with a period of 2, the first term must be the same as the third term, and the second term must be the same as the fourth term. And with those 2 bits, you might not even need all those bits. We should be able to then kind of go backwards and find out what the terms actually are. So I'll go through 4, and I'll give you a couple more minutes to do 5. As soon as it loads again. Cool. So, yeah, we're going to find the first few terms there. So we know the first term is 5. U2 will be P times U1, so P times 5, plus Q, and we know Q is 10, so plus 10 there. The third term is going to be the second term times by P, so P times 5 plus 10, and then plus a 10 on the end. And then U4 is going to be all that times P plus 10, so P times 5 plus 10 plus 10 plus 10. Right, we don't actually need the second and fourth. We can just do this looking at the first term and the third term. So I'm going to set the first term equal to the third term and then try and solve it. So we'll say 5 equals P times 5P, just rearranging the letters there, plus 10 plus 10. So I'm going to expand this and get it all on one side. So 5 equals 5p squared plus 10p plus 10. Take 5 from each side. 5p squared plus 10p plus 5 equals 0. In other words, p squared plus 2p plus 1 equals 0, which is going to be p plus 1, p plus 1. So therefore p is minus 1. And if we wanted to, we could quickly check that. So we can put that into the third, fourth, and second term. So minus 1 times minus 5 plus 10. Minus 5 plus 10 is 5. So 5 plus 10 is 50. Hang on. Let me check that out. Minus 1 times minus 5 plus 10 plus 10 gives me overall minus 5 plus 10, which is 5. So yeah, U3 does equal 5. And we could try that again with U2. U2 is going to be, looks like 5 as well. Is it really periodic with order 2 then? I make it periodic with order 1, but I think all the terms are actually 5. Yeah, to be honest, I think this is every term is 5, but whatever. No, not a great question. All right, I'll give you guys a couple minutes to do the next one. So this one's going to be in degrees, so you can see the little degree symbol there. So be careful that, make sure your calculator is actually in degrees. Find the first few terms, work out the order, and then see how you're going to do part B. So I'll give you guys 3 more minutes to try and do that. Could I have some comments and replies in Teams, please? Right, start now. Cool. Right. Add any replies. So George, yeah, got your answer. Cool. Harry. Cool. Lucy. Yeah, you guys have all got the same thing. All right, let's go through this then. So the nth term is cos of 90 times something. Find the order of the sequence. Okay, so if I find the first term, cos of 90. So use calculator for this. Let's make sure you're in degrees. Cos of 90 gives me 0, so first term is 0. Cos of 180 gives me minus 1. Cos of 270 gives me 0, and the next term is also going to be minus 1. No, hang on. No, sorry, the next one is 1, and 0, and minus 1, and 0, and 1. So what's the period of this? Well, this is going to have a period of 4. 0, minus 1, 0, 1, 0, minus 1, 0, 1. So the order equals 4 there. Yep, which I think you guys have all got. Yep. Good. Find the sum of the first 444 terms. So, question is 444 divisible by 4? I think it probably is. Yeah, so there's 111 periods there. So it's gonna, if we add together one period, we're gonna get 0, minus 1, plus 1, plus 0, which all cancels out to give us 0. So we're gonna get 111 lots of that. So the sum there is going to turn out to be 0. Does that make sense for everybody? 0 plus minus 1 plus 0 plus 1. We've got that period times 111, which is 111 times 0, which is still 0. Cool. A message from Danny there. Yeah, nice lost words. Cool. Right, we're going to do one more and then move on to the next topic. So if you guys could try this one. Same kind of idea, work out the first few terms, see what's going on, and go from there. So I'll give you guys 4 minutes to do this one. And remember, everybody comment or I will be deleting some attendance. Right, let's go through this. So, got a few answers. I'll have a look through those in a minute. I think you guys got the same thing. Okay, so Stroke's periodic state disorder. So the first term is going to be the first term is P. The next term is going to be 1 over P. The next term is going to be 1 over P, which is P. The next term is going to be 1 over P. Next term is 1 over P, etc., etc. So the period is 2. For B, find the sum of 1 to 1,000 lots of this. Well, that's going to be 500 lots of P plus 1 over P, which is going to be 500 lots of that would be P squared plus 1 over P, which I guess that's all we can really write for this. We could say it's 500 P squared plus 500 all over P. Either of those I think would do the job. Right, let's see what you guys got for that. So, who was first? George. Yeah, nice, George. Good. Louis. Yep, slightly different way of writing it, but yeah, fine. Lucy. Yep. Chloe. Yep. Elliot. Got your series, just need your sum. Good job, though. Danny. Nice, yeah. Just make sure all of you are commenting, please, guys. Yeah, good. Okay, that is sequence of the series done. So this week, we've got to be quite quick this week because I think it's ILP day on Wednesday. I haven't actually been told, but yeah, I think it's ILP day on Wednesday. So I think you guys don't have any lectures on Wednesday. Can you confirm that if you've heard that? Because I've heard that, but I haven't seen it written down anywhere. So if you guys have heard that for sure, let me know. But yeah, so today we're going to be starting what's called numerical methods. As soon as this loads. Yeah, cool. Right, thanks, guys. It says, yes, we only have 2 lectures. Oh my god, and we've used half of this lecture already, so it's going to be pretty rapid. So that's one thing. The other thing is on Friday we might have one of the governors in watching. So yeah, it won't change anything. But if you guys could make sure you're asking lots of questions on Friday, I want to show to them that you're all here and paying attention. So yeah, we'll have someone in watching us on Friday. So yeah, if you guys could do lots of commenting, that'd be great. Cool. So starting the new topic, numerical methods. So the whole of numerical methods is about using, it's kind of about solving mathematics without algebra. There will still be a bit of algebra, but the idea is we can kind of brute force our way to solve equations. And this numerical methods is how your calculator does things. The calculator doesn't know any maths. The calculator just has some numerical methods programmed in, which it just loops and runs and iterates until it finds the correct answer. So the first one we're looking at is, well, all of the topics here, we're trying to find roots. So numerical methods, all of this stuff we're looking at solving solving equations / finding roots. And the first kind of method we're going to look at for that is if we imagine a quadratic. Let's say there's a root between A and B. Okay. If there is a root between A and B, what must be true if there's a root between A and B? What do we know based on our knowledge of equations and based on our knowledge of graphs? What's going to happen between A and B on this graph that will prove there's a root? So could you guys have a quick think about this? I'll give you 2 minutes to see if you can think of what I could finish this sentence with. If there is a root between A and B, what? So 2 minutes, what must be true? Just see if you can come up with this one. Cool. Anybody? I don't think anyone's replied. No. Any ideas, guys? If there's a root between A and B, what must be true? I'll wait 10 more seconds. Any ideas? A plus B over true? No. Because A, I could move A here. I could move A, keep U where it is. I can move A there. And the thing I'm looking for will still be true if I move A. So nice idea, Lucy, but no. Any ideas? If there's a root between A and B, y equals 0. Y equals 0 at the root, Elliot, yeah. But I'm talking about the points A and B. What do we know about A and B? How about if I draw some lines here? No, Louis got it. So A has this y value here. B has this y value here. So if there's a root between A and B, f of A, f of B must have different signs. Yeah, you'll see that. A is negative, B is positive. If we choose 2 points either side of a root, there must be a sign change because there must be a point between those two where the gradient goes, where the y value goes to 0. So let's write that out formally. So this is our first numerical method. So here's the mathematical speak. For a continuous function f of x, if there is a root in the interval AB, then there must be a sign change from f of A to f of B. So for a continuous function f of x, if there is a root in the interval AB, there must be a sign change from FA to f of B. Cool, that all sounds good. What do I mean by continuous function though? Any ideas? So 30 seconds. What do you think a continuous function is? No, 26 seconds, whatever. Right, any ideas? What is a continuous function? There's a y value for every x value in the domain. Yeah, nice, cool. So a continuous function basically means there's no asymptotes, no weird bits where bits aren't mapped. To be honest, I can slightly alter this if you want to kind of add underneath this. So I just realized maybe we can make it a bit better. For any function that is continuous in the interval AB with a root in the interval. Yeah, so the function itself doesn't need to be continuous. It just needs to be continuous between those 2 points, and you'll see why in a minute. So, for example, we're going to look at this question. I'm giving you a cubic. Explain how the graph shows there's a root between 2 and 3. So just talking about the graph. Then we're going to try and show f of x has a root between 1 and 2, and then show that the root is 1.4 to 1 decimal place. So I'm going to go through this one as an example. So explain how the graph shows there's a root between 2 and 3. Well, looking at the graph, how does that graph show that there's a root between 2 and 3? Well, it crosses the axis there. So there's our root. It crosses the axis. So graph crosses axis between 2 and 3. Could even say crosses the x-axis between 2 and 3. That's all you need to write for that one. Okay, show it has a root between 1 and 2. So to show that, I'm going to use what we were just looking at on the other page. So I'm going to say f of 1 is 1 cubed minus 4 lots of 1 squared plus 3 lots of 1 plus 1. So f of 1 is 1, take 4, plus 3 plus 1. So 4 take 4 plus 1 is going to be overall f of 1 equals 1. Now I'm going to do f of 2. It's going to be 2 cubed minus 4 lots of 2 squared plus 3 lots of 2 plus 1, which is 8 take 16 plus 6 plus 1. So if I work that out, we're going to get what, minus 10. We're going to get minus 1. So f of 2 gives us minus 1. So there is a sign change in interval 1, 2. The function is continuous. Continuous in the interval 1, 2. Therefore there's a root. So I've written over that. So because there's a sign change, and because the function is continuous, you can see there's no asymptotes between 1 and 2. It's all there. The function is fine. Therefore, there's a root. Okay, last bit. Show that the root is 1.4 to 1 decimal place. And the trick here is it's mentioned 1 decimal place, so it needs me to show this with some precision. So whenever you get a question like this, asking you to show it to some precision, we're going to look basically one more decimal place. So look to one more dp accuracy. So I'm going to do f of 1.45 and I'm going to do f of 1.35. So I'm going to go slightly above, slightly below 1.4, and we're going to go at bits that would round. So 1.45 would round to the next value. 1.35 is the lowest value that would round to 1.4. So look at the kind of top and bottom of the range of values which would round to 1.4. So for this I'm going to want to use the calculator. So I'm going to do 1.45 cubed minus 4 lots of 1.45 squared plus 3 lots of 1.45 plus 1. And if I work that out, I get minus 0.0114. Going to do the same thing with 1.35. And this time I get 0.2254. So, because I've shown, therefore, sign change, so therefore the root equals 1.4 to 1 decimal place. So if we've proved that there must be a root between a greater degree of accuracy, we can assume the root would round to 1.4, because it must be somewhere in the middle, somewhere in between 1.35 and 1.45. Whatever it is would round to 1.4. So that's why we go 1 decimal place accuracy, because then we know anything in the middle of those values will round to 1.4, which is the value we're trying to prove. Alright, let's get you guys trying one of these then. Oh, hang on. Before we do another one, there's a few cases where this won't work. So, can you guys have a quick look at these and try and decide why these won't work with a reason? So, if I label these A, B, and C, Why won't our looking either side of a root work for these three cases? So I'll give you guys a minute to have a think about these. Cool. All right. Any ideas then? A, B, C. Why won't these ones work? So if you think about A and B, for the first one, there will be a sign change. But the problem is there's more than one root. So you're not going to know which root you're finding. So more than one root. So really your interval is too big. Interval too big. Okay, what's wrong with B? B is not continuous as an asymptote. So in other words, for B, there is a sign change, but there is no root. There's a sign change between A and B, but there is no root between A and B. I shouldn't really have drawn B where I did, because it looks like it does have a root there. So if I redrew the function, that's what I was really getting at, is that between A and B, there is no root. There is a sign change, but there is no root. And for part C, the sign doesn't change, but there's actually two roots. So sign does change. Two roots. Sorry, no, the sign doesn't change. What am I talking about? Sign doesn't change, but there are two roots. Again, your interval is too big for that one as well. Cool. So you could, if you like, just try loads of values and eventually try and find a root by just honing in on roots, by taking successive decimal places either side. All right, so let's get you guys trying one. So I want you to sketch these two, decide how many roots there are to the solution of these. Show root lies in the interval 1.7 to 1. Should be 1.8 there. I'll just quickly rewrite that bit. And then show the root is 1.763 to 3 decimal places. Could you guys try this one? I'll give you 4 minutes for this. It is a little bit trickier. You have to kind of put them together into one equation, but let's see how you get on. So 4 minutes starting now. Ask for help if you need it. Cool. Yeah, so as George has commented there, how many roots? What it means is, sketch it first of all. So we got 1 over x, which is going to be here, and we've got ln x, which is going to be here. How many roots? So I mean how many roots to the equation ln x equals 1 over x. And you can see on the graph there is 1 root because it crosses once. So 1 root. So it crosses once. Show a root lies in that interval. Okay, so this is slightly harder. So what I need to do, I need a function to put it into. So I'm going to get ln x, 1 over x, all on one side. So we're going to say f of x is ln x minus 1 over x. So if we can show there's a sign change in the interval of that function, it shows there must be a root. So we're going to do f of 1.7, and we're going to do f of 1.8. So calculator out, ln of 1.7, take 1 over 1.7, which gives me minus 0.057. 0.058 if I'm rounding. And do the same thing with 1.8, which gives me 0.032. So there's a sign change in that interval. So therefore, root, and we can say it's continuous in the interval as well. Yep, so it's continuous. To find a function, that's the only hard bit of this one really. Because we've got two things equal each other, to find a function I need to get it all on one side and say it equals 0, and then we can do it like this. Okay, show the root is 1.763 to 3 decimal places. So I've just wrote out the function, didn't mean to do that. So again I need to do the so f of x ln x minus 1 over x. So I'm going to put in, I'm going to do f of 1.7635 and f of 1.7625, so slightly above by 0.5 and slightly below by 0.5. So then we're going to do ln 1.7635 minus 1 over 1.7635. And we get 2.46 times 10 to the minus 4. Do the same thing with the negative, sorry, with 2.5 instead. And this time we get minus 6.43 times 10 to the minus 4. So again, sign change. Therefore, root is 1.763 to 3 decimal places. All right, has anyone got any questions about that before we move on to another one of these? Okay. Right, so there's 2 here for you guys to try, which is 10 marks worth of question. So I'll give you guys 10 minutes to try and answer these. Please comment if you need help. Again, not all of you are commenting, so we're going to have to look over the attendance and see who's actually here. But make sure you're leaving comments if you are here, guys. Even if they're just asking for help, that's fine. You can send them on the group one, or you can message me individually if you want to. Ask for help if you're stuck, and also send me pictures of your answers when you got them. So 10 minutes starting now. Cool. Have I been sent any? I have been sent to Lucy and Chloe. Thank you, you two. Alright, the rest of you can get this in as soon as possible. Let's start getting through this. So, show the equation has a root between 1.4 and 1.5. Okay, so we're going to do h of 1.4. And h of 1.5. So doing the cube root of 1.4 minus cos of 1.4 minus 1. It tells us x is in radians. And the same thing with 1.5. Right, so cube root 1.4, take away cos 1.4 take 1, don't forget to make sure you're in radians, and we get minus 0.051. Do the same thing for 1.5. And we get 0.074. So yeah, continuous plus sign change, therefore root. Right, by choosing a suitable interval, show the root is 1.441. So we're going to do the same thing again, but with 1.4415. And f of 1.4405. So same idea. So for this one we get 6.9 times 10 to the minus 4. Or 6.99, let's say then. And same thing for 4405. And we get minus 5.54 times 10 to the minus 4. Same reason, continuous, sign change, therefore root. We also need to say root is 1.4412 dp. Cool, so that's the first one. Second one, very, very similar. We'll go through this nice and quickly. Oh dear. So, yeah, we're going to do sine, or we're going to do f of 2.2 and f of 2.3. Then we're going to do f of 2.2195 and f of 2.2185. So let's do all this at once. So we're going to do sine 2.2 minus ln 2.2, 0.02. Change it to 2.3 minus 0.87, 0.087 even. So yeah, therefore sign change, therefore root. We'll do the same thing with the other bits just to speed us up a bit here. Minus 4.1. Minus 4.14 times 10 to the minus 4, and same thing 2.285, 6.4 times 10 to the minus 4. So again, therefore root 2.1219 3dp. Cool, so both exactly the same there. Right, let's have a quick look through your answers. So, George. Wait, who was first? I think Guy was first. No, Chloe. No, Lucy. Oh, yeah, of course, Lucy and Chloe. Yeah, good. Chloe, good. Guy. Yeah, good. George, good. Elliot. Elliot, yours are coming out. Oh wait, no, that's the first one. Yeah, good. Yeah, cool. Well done, all of you. Okay, really quickly we'll start this one, and we'll talk about the rest of this on Friday. So that was the first topic we just did in numerical methods. The next point is called fixed point iteration. And the way we use this, again, it's another method for finding roots. So the way we do this is we set the function equal to 0. We then rearrange the function. So set function equals 0. We then rearrange function to get x equals f of x, which is weird, okay? We're rearranging a function to get x equals f of x. I'll show you what I mean by that in a minute. And then we turn it into we call this the iterative formula. So once we've got the function in the form x equals the function of x, we then turn the x on its own into xn plus 1. In other words, the next value is function of the first value, and then we try a starting value. So I think we'll start the first bit of this, and then next week we'll actually get into it. So for example, f of x. Alright, so for example, let's say we're trying to solve x squared minus 3x plus, maybe not plus 2, minus 10 equals 0. So that's my equation we want to try and solve. So step 1, write it as f of x equals 0. Well, that's done already. So we've done first step there. Next bit, rearrange it to get x equals. And there's 3 different ways we can do this. So way number 1, I'm going to get my x squared on its own. So we're going to go x squared equals 3x plus 10. Square root both sides, therefore x equals the square root 3x plus 10. So that's done. Then we can say, write it in the iterative formula, xn plus 1 equals the square root of 3xn plus 10, which is kind of like a recurrence relationship like we looked at earlier today and last week. Yeah? And what this will do then is if I choose a random starting value, we're going to put a value in as xn, hit equals on the calculator, and it'll find me the next one. So I'm going to bring up the graphical calculator and show you what happens. Now, I haven't tried this, so I'm hoping this works. It doesn't always. Where's my calculator? There it is. Should appear above in a second. Cool, there we go. Alright, so I'm going to go to standard calculator. Let's delete all this quickly. Alright, so I'm going to type in, first of all, the easiest way to do this is to use the answer function in the calculator, because then we can just keep spamming equals and iterating. So I'm going to use my first x value, x0, or x1, let's call it. What should we use? I'm going to use 0.5. I like the sound of that one. I don't know if this will work, but we'll go for 0.5. So I'm going to just type in 0.5. I'm going to type in 0.5 and hit equals. Yeah. And what that's done is that's kind of saved my answer. So if I do shift an answer, we can check my answer is 0.5. So I'm going to use answer kind of like as x. Right, so if I type in square root of 3 lots of the answer plus 10, I can hit equals, and that will find me my first or my second x value, if you like. So I've put 0.5 in here, times it by 3 plus 10, and then square rooted it, and that's going to give me my next value x2. So I'm going to write that down as x2, and we can push the SD button to get it as a decimal. So the next value is 3.39. Yeah, I'll skip all the gunk on the end. What we can do now is I can hit, can I do this? Am I making things up? I can go back up to this line and hit equals again. Oh, I can I do this equals now? Here we go. I just hit equals again and again and again. So the next value, x3, is 4.49. Hit equals again. We now get 4. Let's make some space here. So 4.49, my fourth value, x4, 4.85. Let's do it again. x5, 4.95. Let's do it again. 4.99 this time. Hit it again. 4.9. That's going to round up. So x to the 7. Technically going to be 5 there. Because actually, if you look, we're not quite getting to 5. There we go, there's 5. And now we kind of lock. So x8 is 5, x9 is 5, etc. So it looks like 5 was a root to my quadratic. So I've started with a random value, 0.5 I just randomly picked, and it's converged to a root, x equals 5. So we've, just to recap what we did there, we started, if I go back actually, maybe I can go back and find it. No, so I could. So we started with a function. We rearranged that function to get x equals a function of x. We then put in a random value of x to generate xn plus 1 using the iterative formula. Right, could you guys just comment if there's anything there that you didn't really understand while I click back to retrieve the last function. So keep clicking back. Have you guys got any questions about what we just did? Because this is what we're going to be looking at on Friday. Very slow. There we go. Cool. All right, let's come back. So, yeah, I mean, x equals 5 is one of the roots, is it? Yeah, so it looks like I've chosen a quadratic that factorizes. There you go. But we can see this found one of the roots. So this might be how your calculator solves quadratics. Okay, real quick, 7 minutes. We're going to try one more thing. Let's see, could you guys see if you can rearrange this to get a different iterative formula? So I got the square, x squared on one side. Could you guys see if you can find a different iterative formula? I'll give you 2 minutes to do that, and then we'll go through, we'll try another iteration with a different formula. So 2 minutes starting now. Can you find a different iterative formula? Cool. Any different rearrangements, guys? I know that wasn't much time there. X squared minus over 3, is that what Elliot's got? Okay, cool. That looks good to me. So Elliot, I believe you arranged it to get 3x equals. So added 3x to the other side, so 3x equals x squared. Take 10. Divide by 3, so x equals x squared. Take 10 over 3. Good. There was one other way, which is often a bit harder, is factorizing. So we could say x squared minus 3x equals 10. X take 3 equals 10. So x equals 10 over x take 3. So those are the last two ways that you can have to rearrange this one. Right, real quick then, let's write in n plus 1 and n. Turn that into an iterative formula. And we'll start with, should we start with the same value or a different value? Let's start with, we'll try 0.5 again. So x1 is 0.5. Let's do this on the calculator up there. So this time we're going to type in, again, 0.5. So that's locked in as our answer. We're then going to do fraction, answer, squared, take 10, divided by 3. So first value, x2 minus 3.25. Let's go again. x3 is 0.1875. x4 minus 3.32. I think this one might take a little bit longer, so I'm going to clear some space here. x5, what was it, 0.344. x6 minus 3.29. x5, 0.28. x6 minus 3.3. I'm just going to spam equals and see if this gets anywhere, because at the moment you can see it's kind of jumping between two values. So if I hit equals a lot, interesting. Can you guys see what's happening? So we're flicking between, if I go really fast, you can see one of the answers is about 3.3 and the other answer is about 0.3. Weird, huh? So, yeah, I'm going to explain what this is doing next lecture, explain why it didn't work. We did the same thing, we rearranged it, got a function, put in the same starting value, but now we're just flicking between two things. Neither of which is root, remember the other root we're looking for is -2, so it's kind of stuck, it's not gone to a root, it's kind of like periodic oscillating between those two values. I could keep going all day and nothing's going to happen, so we'll scroll up. Yeah, nothing's changed. So we'll talk a bit more about this on Friday. As I said on Friday, please make sure you're there on time and do lots of commenting because we've got someone watching. Yeah, we'll talk a lot more about what this fixed point iteration thing is. Maybe go into chaos theory if there's a bit of time, and then we'll be looking a bit about the Newton-Raphson method as well. Right, cheers guys. I'll speak to you on Friday. Have a good ILP day on Wednesday. Thank you. Bye.